In this section of the Quick Start video, we will go over some ways you can use Pipeflow to answer common questions about your systems. In this first part, we are going to demonstrate how you can use Pipeflow to size a pump for your current system and for future expansion. In the model we have here, we are pumping a fluid from a storage tank and discharging it to atmosphere. There is a plan to increase the amount of fluid that will be discharging up to 800 gallons per minute. But for the first year, the process will only discharge 500 gallons per minute. We want to size the pump so that it can operate in both these settings. The first thing we need to do is create a new lineup of the model so we can see how it will operate in both scenarios. To create a new lineup, you can select the lineup button here or from the system drop-down menu. Next, we will click New to create a copy of the design case. Once created, we can then rename the lineup for our convenience. I am going to rename the lineup Final Operation and select OK to close the dialog. Now I have two scenarios in the lineup drop-down. I'm going to select the new lineup and change the settings to 800 gallons per minute. We will now calculate my system and see how the pump is operating. In our design case lineup, the pump is operating with a flow rate of 500 gallons per minute and a total head of 24.58 feet. In our final operation lineup, our pump is operating on a flow rate of 800 gallons per minute and a total head value of 39.31 feet. I am now going to select a pump for both operations. I'm going to right-click the sizing pump and choose Select Catalog Pump. Once the pump selection window opens, I'm going to select the manufacturer's catalog for the pump I want in my system. Then I will specify the speed for my pump. As you can see, some pumps have already filled into the list as possible pumps for my system. Now I need to make sure these pumps will work for both operations. To do this, I will click the Edit Search Criteria button and add my second operating point of 500 gallons per minute and approximately 25 feet of head, and then click OK to send the new operating point back. Now we have two design points on our selection list, and I will choose the pump that will give me the best efficiency for both operations. I will select the best pump and then click Select Pump to send the pump information back to Pipeflow. Now we can see that the pump operation has changed to fixed speed for both lineups, and both pumps are operating off of the selected pump curve. Since these pumps are operating in VFD mode, I am now going to set them to their correct flow rate. 500 GPM for the design case and 800 GPM for the final operation lineup. Once changed, we can see that we have no messages for our system and that the pump is operating very well at both flow rates. Next, we will see how Pipeflow can be used to determine the position of a valve to balance the system, cutting days off of the balancing process. In addition, we will see how balancing the system can provide extra system capacity, along with minimizing the system's pumping cost. In looking at the flow sheet, you can see the system takes suction from the cooling tower sump through one of two circulating water pumps, then to 3 buildings. Each building has 4 cooling loads requiring varying capacity. After exiting the heat exchangers, the fluid goes through a throttle valve, then a common return line to the spray header of the cooling tower. Building 123 was recently added to the system. The circulating water pumps CCW15 and CCW16 were sized so one pump could supply the entire cooling loads, including the Building 123 expansion. After 6 months of operation with Building 123 online, the circulating water pump CCW15 tripped due to excessive electrical load. To correct this problem, operations started running both cooling water pumps continually. Since then, there have been no problems. The plant's engineer at this site was instructed to add a third circulating water pump as a standby to improve the system reliability. Before adding the third pump, the plant engineer wanted to get a better understanding of why the existing pump arrangement would not meet the loads as designed. When using a single pump, it can be seen that the flow rate through the pump CCW15 exceeds the pump's runout of 2,351 GPM, which is why the motor for the single pump tripped on overload. When looking at the system with 2 pumps running, we can see that neither pump is in a runout condition, explaining why the pumps no longer trip on overload. Notice, however, that many of the components are yellow, indicating the flow rate through those components exceeds the manufacturer's limits. This could cause a problem over time due to high fluid velocities in the heat exchanger tubes. After a trip to the field, the plant engineer noticed all the throttle valves were wide open, and further investigation discovered that the system was never rebalanced after Building 123 was added to the system. Before sizing the third pump, the plant engineer decided to use the computer model to see if a balance system was possible using a single pump, as originally designed. To adjust the flow rates to the design values, balancing valves in each loop are throttled to increase the differential pressure across the loop, thereby lowering the flow rate in that loop. This also causes the flow rate in the adjoining loops to increase, resulting in increased differential pressure in these. To balance the system, all the valves must be throttled, and the system results checked multiple times until the flow rates through each loop are at the design value. This is a tedious and time-consuming process when done by trial and error in the field. To accomplish this in PipeFlow, FCVs are inserted into each loop and set to the design flow rate. The program then calculates the differential pressure across each throttle valve needed to balance the flow for each loop. This table shows the design flow rate for each load in the system, and therefore the flow rate to set each FCV to. As you can see, I have already set the FCV to the correct design flow rate, and the system is balanced. The total flow rate through the system is now 2,055 US gallons per minute, which is less than the run-out flow rate for the pump. As you can see, the system can run with only one CCW pump in operation. This eliminates the need to purchase and install a third pump. By having only one pump operating, we also save on annual pumping costs. Finally, the system only requires 2,055 GPM, which is well within a single pump's operating curve, giving the plant future system capacity as well. In the final part of this video, I want to show you how you can use PipeFlow Professional to determine how and whether an expansion will fit within all the elements of an existing infrastructure. Cooling systems capabilities can fall into this category, as there are often multiple solutions to any expansion project. Consider the following example as a case study in miniature. The addition of 2 more racks to an existing coolant distribution unit, supporting a bank of 4 rear door heat exchangers. The chill water supply is 40 degrees Fahrenheit, and the return is set at 60 degrees Fahrenheit. The tubing inside the cooling distribution unit connects to a manifold supplying 62 degrees Fahrenheit water to the rear doors, with 74 degrees Fahrenheit returning through the return manifold. The rear door heat exchangers are required to pull 10 kilowatts from the exhaust air of each cabinet. As the chill water system and the cooling distribution unit have ample thermal capacity, the manifold inlet valve is set at 45% open, and the individual control valves for the heat exchangers have all been manually set to the 70% open position. Here is a model of the system in operation. The first attempt may be to open all the control valves to compensate for the additional load, especially since the manifold inlet control valve is halfway closed and we're only increasing the thermal load by 50%. Setting the manifold inlet control valve at 95% and the individual rack control valves to 90% provides the overall 60 kilowatt cooling required at the cooling distribution unit. However, now only 2 of the 6 racks are getting the 10 kilowatts they need. We can try to manually balance through a number of trials, but that is tedious and requires multiple iterations. With the new thermal control feature in PipeFlow Professional, we can set the control valves to provide the flow required to each rack to cool 10 kilowatts. Doing this, we find a problem. We have exceeded the capability of the control valves for the 2 added units and one of the previously existing units. How can we solve this? There may be a temptation to upgrade the cooling distribution unit to a higher thermal capacity or change out the control valves. But are we jumping to conclusions? Using the gradient color feature, we can look at the hydraulic bottlenecks, areas of high head loss, to help determine the best course of action. At first glance, it appears the key elements are the control valves in the cooling distribution unit. But if we narrow the range for head loss to see only pipe sections, which is 0 to 5 feet, it reveals we have a significant loss in the first section of both the supply and return manifold headers. This leads us to some alternatives. The manifold system appears undersized for 6 rear door heat exchangers, and we could replace the 3/4 inch manifolds with 1 inch tubing as shown below, which reduces the head loss and easily achieves the 10 kilowatt per rack desired. However, an even lower cost alternative is, instead of connecting the new loops to the far end of the headers, we change where the supply lines attach to the headers. We can achieve this by either expanding the header in the other direction or moving the supply lines to a different node, as shown below. Now we can add the two racks with minimal modification to the system. While this is a small example, Pipeflow Professional can perform similar analysis on your system, and there is no limit on the number of pipes or devices. With Pipeflow Professional, even large-scale projects can be manageable and efficient. This finishes out the section on ways Pipeflow can be used to answer many different questions you have about your models. Please return to the main Quick Start page for other videos on the Pipeflow Professional program.